Periodic trends. There are periodic trends in the table. These are not hard and fast rules. They're more generalizations, but they're useful, right? We use a lot of generalizations like this in everyday life. Sometimes they're called a rule of thumb. You know, who's going to be larger, a second grader or a third grader? The third grader. Are all third graders larger than all first graders? No, but most of the time, right? So these periodic trends are like that. They're usually true, but not always, but they're still useful, right? So one of the trends is atomic size, the size of an atom. There are different ways to define atomic size. We're not going to go into that, but basically it's the distance between the outermost electrons and the nucleus. That kind of makes sense. Okay, the distance from the middle of the atom to the farthest electrons. So really it's a radius, the radius of the atom. So we need to be able to remember what these trends are. Some of them make sense. They're intuitive. Well, of course. So if we go down, oh, that's on the next slide. Some of them are counterintuitive. Going across a period from left to right on the periodic table, the atomic size decreases. This is not what you would necessarily expect, right? Sodium has 11 electrons and 11 protons. Argon has 18 electrons and 18 protons. We would expect argon to be bigger, wouldn't we? But it isn't. It's smaller. And knowing about electron configurations can help us to understand that. Where are the valence electrons? What level are the valence electrons for sodium? 3, level 3, right? Because sodium is in period 3. How about argon? Where are the valence electrons? Also in period 3. Okay, so this is where thinking in the Bohr model is a little more convenient. So let's compare sodium and argon. So sodium has 11 protons. And it's got, there's the second level that has 2 electrons in it, and there's the third level that has 10 electrons. That's 4, 5, 6, 7, 8, 9, 10. And then there's the third level, and it has 1 electron. So this is sodium. Argon has how many protons? 18. 18 protons. It also has 2 electrons in the first level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons in the second level. How many electrons in the third level? 10. No, 8. Sorry. Just testing you. No, I wasn't. I lost my mind. 2, 3, 4, 5, 6, 7, 8. Argon. This third level in sodium is going to be roughly the same distance from the nucleus as the third level in argon. The 3s and 3p orbitals are roughly the same size until you talk about the attractive force of the nucleus. So here in the nucleus, we have 11 protons pulling on this electron. Here, the electrons are being pulled by 18 protons, which is a stronger attraction. 18. If you were offered 2 jobs and one paid you $11 an hour and one paid you $18 an hour, which one would you be more attracted to? $18 an hour. The attraction between these negative electrons and the positive protons is greater here. Greater attraction, those electrons get pulled in. So as we go across a period from sodium to argon, The electrons are being put into the same principal shell, the third shell, but the charge on the nucleus is increasing. That increased charge pulls the electrons closer and makes the atoms get smaller as we go across. So as we go across, the number of protons in the nucleus is increasing, which increases the pull on the electrons and causes the atomic size to shrink. Going down a column in the periodic table, this one makes sense. Moving down, the highest principal quantum number is increasing. So lithium has valence electrons in the second level, sodium has them in the third level, potassium has them in the fourth level. As the principal quantum number increases, the size of the orbitals gets larger. And so as you go down any column, the atoms get larger. So that one makes sense, but going across is opposite what you might think. So here is a graphic representation of all of this. So here's lithium, and we see as we go across, they get smaller. Sodium to argon. Potassium, smaller and smaller and smaller to krypton. As you go down, they get bigger. Any column you pick, they get bigger as you go down. Any questions? You're going to need to be able to predict, based on looking at the periodic table, which of a pair of elements has the larger atoms. So we'll do a little practice here. So choose the larger atom in each pair, lead or polonium. Well, we have to find them. So here's polonium, and here's lead. They're in the same period, in the same row. The trend is, as you go across, the atoms get smaller. So which is bigger, PB or PO? PB is bigger. So lead is bigger. Let's compare rubidium and sodium. Here's rubidium, or sodium. What's the trend as we go down? It gets bigger. So which one's larger, rubidium or sodium? Rubidium. Okay, tin or bismuth. So here's bismuth, and here's tin. Well, all those guys are different. They're in different columns and in different rows. Well, let's think about it. So we have a trend going across that would predict that bismuth is smaller than tin, right? But we have a trend of going down that says that bismuth would be larger than tin. Those are conflicting. So the best I would expect of you is can't tell. You can't tell just by looking at the periodic table. How about fluorine or selenium? Well, let's see. Here's fluorine, and here's selenium. Again, we don't have a single column or a single row. But let's look at the trends, and maybe they'll reinforce each other. So fluorine is to the right of selenium. As we go across, elements get smaller. So that predicts that fluorine is smaller. The other trend is that as you go down, things get larger. That also predicts that fluorine is smaller. So we can predict this one. Fluorine is smaller. That means that selenium is larger. Any questions? Another trend is ionization energy. What the heck is ionization energy? That's the energy needed to remove an electron from an atom in the gaseous state. So to make an ion out of sodium, we have to remove an electron. So sodium plus some amount of energy gives us a sodium ion, and an electron. The sweater does not fall off of sodium. He has to take it off, right? There's some energy that has to be expended in order to take that electron away from sodium. It doesn't just fly away on its own, okay? It requires energy. The trend in ionization energy is the opposite of the trend in size. And one way to remember this is to think about, well, who's more willing to lose an electron? A group A? Group A. They're all group A. Group 1A element or a group 7A element? If you remove an electron from a group 1A element, it all of a sudden has a noble gas electron configuration. Is it going to be happy about that? Yeah, that's great. Oh, you're going to take my sweater? Oh, cool. That's great. I'm going to give it up very easily. What about group 7A, like fluorine? If fluorine loses an electron, does it have a noble gas electron configuration? No. It's gone one step away from what it wants. Is fluorine going to give up an electron very easily? No. It's going to be very difficult to remove an element from fluorine. So as you go across a period, the amount of energy needed to remove an electron increases. As you go down, the amount of energy needed decreases. And it's not a coincidence that it's opposite with the size. Okay? For a larger atom, the electrons are farther from the nucleus, right? So the force of attraction between them is going to be weaker than between two like charges that are closer together. So if we have a positive and a negative that are close together, or a positive and a negative that are far apart, which one has a stronger attraction? The ones that are close together. Okay, so the electrons of small atoms are held more tightly than the electrons of large atoms. You've all put magnets on the refrigerator, right? You get a piece of paper from school and you stick it on the fridge. And then you don't get around to doing anything about it. And you got another piece of paper you need to stick up there, so you just put it under the same magnet, right? And it holds, but how many pieces of paper can you stick under that magnet? Depends on the magnet, but 3, 4 maybe, unless you've got a really strong magnet. Why doesn't it work anymore when you get 5, 6, 7 pieces of paper? Because the paper is causing the magnet to be farther from the metal door of the refrigerator. As the distance increases, the force of attraction decreases. So as we go down a column, the outermost electrons are farther away, they're easier to pick off. I have a very politically incorrect analogy for this, and it's appropriate right now because the big Fresno Fair is going on. I saw some people at church last night, and they were, oh, aren't you going to the fair? And I'm like, no, I am not going to the fair. I view the fair as an excellent place to lose a child, right? Now, 2 of mine are away at college, but if I went to the fair with 4 children in tow, I only have 2 hands, right? They're going to run off in all different directions. A friend of mine who only has 1 child, if we all went to the fair, she's got her 1 kid by the hand. Which mom is it easier to snatch a child from? Me. Andrew is just going to get snatched. This other mom has 1 child, right? She's focused on this child, and if somebody took him, she would notice. If you took one of mine, I might not notice for a while. The thing about my kids is, though, that they're ornery enough that if someone did take them, just like in the Dennis the Menace movie where the bums kidnapped him, they brought him back because he drove them crazy. So I'm not too worried, but I'm still not going to the fair. Okay, enough of that. So here's the trend. I think it's better to understand these trends, because then on an exam, when you kind of lose your mind, right, you can think them out. and reason them out. The other way is just rote memorization. Ionization energy increases across, decreases down. Okay? That works for some people, and if that works for you, great. Doesn't work for me. But ionization energy decreases as you go down in a column, and it increases as you go across. So then we have very similar questions here. Choose the element with the higher ionization energy in each pair. So we find them on the periodic table: magnesium and strontium. Which one has the higher ionization energy? The magnesium. The trend is that as you go down, the ionization energy becomes smaller. How about indium or tellurium? And you don't need to know their names to answer these questions. There's tellurium and there's indium. In and tech. Higher ionization energy is tellurium. As you go across, the atoms get smaller and the ionization energy gets stronger. So higher ionization energy would be Te. How about carbon or phosphorus? Well, we got to look at the trends. Here we've got a diagonal thing going on. As we go, the wrong place. As we go across, ionization energy gets larger. That predicts that phosphorus has the larger. As you go down, it gets smaller. That predicts that phosphorus is going to be smaller. So those two trends contradict each other. Can't tell. I know that bothers some of you. It's okay. There could be, yes. There could be. Fluorine or sulfur? Here's fluorine, here's sulfur. Again, we've got the diagonal. We just have to look at both of the trends. Going across, ionization energy gets stronger. Fluorine should be stronger. As it goes down, it gets weaker. Sulfur should be weaker. Fluorine should be stronger. So they both predict that fluorine would have the larger ionization energy. So that one's going to be fluorine. Okay? Metallic character. This one's a lot easier to remember. So by metallic character, we mean how it is more like a metal, right? And I've told you before, we've got masculine and feminine is how I think of them. Metals are masculine, non-metals are feminine. And so we have this stereotypical idea of what masculinity is, right? And so you could take any one individual male person and say, well, this guy is more masculine than this other guy, right? And that's kind of what we're looking at. It's not that one is not a metal and one is a metal, but which one is more a metal. And one of the characteristics of metals is that they tend to lose electrons, and nonmetals tend to gain them. As we go across a period, the ionization energy increases, which means that electrons are less likely to be lost. So that's the more scientific explanation of the trend, that metallic character decreases as you go across a period, and it increases as you go down. It follows the same trend as atomic size. But this is how I think of it. So the yellow ones here are the metals, right? And the nonmetals are green. So if I'm going across, say, period 4, metal, 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 semi-metal, non-metal, I went from metals to nonmetals. Metallic character decreases as I'm going across. Does that make sense? If I go down a period, I'm starting with nonmetals, semi-metal, metal. Metallic character increases as you go down. Okay? And then, again, with very much the same questions. I'm just going to do 2 of these because I'm sick of them. Tin or tellurium? Here's tin, here's tellurium. Which one is more metallic? Well, this one's actually a semi-metal, right? It's not even a real metal, and that one is a metal. As we go across, they become less metallic. Tin is more metallic than tellurium. How about selenium or iodine? He's going to fall down the stairs on that skateboard. Someone else will have to call 911 for him. How about this one? Well, as we go across, they become less metallic. As they go down, they become more metallic. Can we tell? Mm-mm. This is a diagonal in the wrong direction. Huh. No, I'm doing letter D. I didn't want to do B and C. So between selenium and iodine, we can't tell. I thought it was going to be C that was the can't tell because it was like that on the other two. But any questions? The same idea. Oh, well, maybe we could do those other two examples. And then we'll just be done. Okay. I didn't know how close I was to the end here. Okay, silicon or tin. Here's silicon and, whoops, here's tin. Which is more metallic? Tin. Carbon's a nonmetal, silicon is a semi-metal, germanium's a semi-metal, tin is actually a metal. As we go down, they're becoming more metal-like, more metallic. So the answer there is tin. And let's do orange maybe. Bromine or tellurium. Here's bromine, here's tellurium. Okay, going across, we get less metallic. So that predicts that tellurium is going to be more metal-like than bromine. As we're going down, we get more metallic, and that also predicts tellurium will be more metallic. So the answer is tellurium.